Hello everyone, my name is Mir Faisal Tarif. My groupmate is Shoaib Mahmood. This presentation introduced the project title AI-based wind tracking and air control system for optimizing wind turbine efficiency. This project focuses on designing an intelligent air control mechanism that uses real-time sensing, online weather data, and AI prediction to improve turbine alignment and overall energy output. The following slides will provide a detailed overview of the system architecture, simulation results, hardware implementation, and the role of AI in enhancing air performance. These slides introduce the overview of the entire project and summarizes the key features of the smart air control system. The system is designed as a AI-based solution to maximize wind turbine efficiency by maintaining accurate air alignment. It integrates 4 wind direction sources: wind vane, live API data, forecast data, and AI prediction, and uses a priority-based fallback logic to keep the turbine operating even during sensor faults or Wi-Fi interruptions. Yaw optimization is achieved using shortest path rotation, a plus minus 15 degree deadband to reduce motor wear, and a plus minus 80 degree cable safe limit for protection. A complete MATLAB simulation model developed to test wind tracking and power output, while the hardware prototype used an Arduino Uno R4 Wi-Fi, a stepper motor, a magnetic encoder, and vane sensor. The AI model training using cosine sine encoding and fine tree regression supports accurate direction prediction when real input are unavailable. Results show stable alignment, higher power output around 3.7 kilowatt, and reduced motor movement. By removing transmitter receiver hardware, the system also reduced total cost by 60 to 70% and provide a reliable, low-cost, fault-tolerant air control solution for small wind turbines. The next slide highlights the key limitation of traditional air control systems. First, systems that rely only on a single wind vane often produce inconsistent or unstable directional readings, especially when the wind is turbulent or shifting rapidly. Over time, vane sensors also develop issues such as noise, drift, and mechanical wear, which further reduce their accuracy and responsiveness. In many setups, transmitter receiver module are used to send directional data, and this component increase overall cost while remaining vulnerable to communication delays or complete signal loss. Traditional air system also lack any reliable fallback mechanism. When the vane falls or provide incorrect data, the entire system loses its ability to maintain proper alignment. Another major drawback is that conventional air control reacts only the current measurement. It cannot anticipate or predict upcoming wind changes, which leads to frequent air correction. This constant back and forth rotation result in higher motor uses and faster mechanical wear on the turbine component. In contrast, the AI-based smart air control system developed in this project overcome all these limitations through multi-sourcing sensing, predictive intelligence, and automatic fallback logic, ensuring continuous and reliable air alignment. Moving on to the importance of air alignment, this slide explains why keeping the turbine facing the wind is critical for power generation. A turbine delivers its maximum output only when the nacelle is directly aligned with the incoming wind. Even a small misalignment reduces the effective wind component hitting the rotor, and the power loss follows the cosine cube law. As table 1 shows, the loss increases very quickly as wind arrow grows. At 5 degrees, the power drop is only about 1%, but by 15 degrees, it rises sharply to nearly 10%. When the misalignment reaches 20 to 25 degrees, loss become increase in the range of 17 to 25%. For this reason, the smart air control system in this project uses a plus minus 15 degree limit. Below 15 degree, the loss is small enough that correcting every fluctuation is unnecessary, but beyond 15 degree the drop becomes significant enough to justify yaw movement. Maintaining yaw error within this plus minus 15 degree range ensure high efficiency, reduce mechanical wear, and keeps the turbine operating smooth under changing wind condition. Now moving on to the proposed smart yaw system. This system integrates real-time yaw control to enhance the turbine's energy collection efficiency. It is built around two major subsystems, the power generation unit and the intelligent yaw control mechanism. A microcontroller handles the yaw correction by using both the physical wind vane data and online wind information. The 12-volt analog wind vane provide continuous real-time measurement of local wind direction, while the microcontroller connects to the open weather map platform through Wi-Fi to retrieve live and forecast wind direction using secure API requests. By combining vane, live, and forecast data, the system can continue operating even when one of the sources becomes unavailable. The controller then calculates the yaw error and sends precise command to the stepper motor driver to rotate the nacelle. A closed-loop feedback structure ensures that the nacelle stays correctly oriented to the wind while avoiding unnecessary or frequent rotation. Overall, this system improves alignment stability, increase total energy production, and adapts effectively to changing weather patterns. This slide presents the yaw control algorithm and outlines how alignment decisions are made. The controller begins by reading wind direction and wind speed for both the wind vane and the online API. It then checks whether the wind speed is above the cutting threshold. If the wind is too low, the system simply waits without performing any movement. Next, the yaw error is calculated as the difference between the nacelle orientation and the incoming wind direction. If the yaw error is within plus minus 15 degrees, the nacelle is kept steady to avoid unnecessary motor wear and over correction. However, when the yaw error exceeds plus minus 15 degrees, the controller activates the stepper motor in the appropriate direction to realign the turbine and recover lost power. After the movement is complete, the controller updates the nacelle position so the system always knows its latest orientation. This entire process runs continuously in a loop to maintain proper alignment and ensure smooth, efficient yaw correction during changing wind conditions. This slide explains how the system decides the direction and method of yaw rotation under different conditions. The first case is shortest path alignment. Here the controller calculates the yaw error and rotates the nacelle along the short rotational path, whether clockwise or counterclockwise towards the wind direction. This approach minimum motor travel, reduces alignment time, and ensures fast corrections. The next case is the plus minus 15 degree deadband with a stability timer. Yaw correction is only triggered when the absolute yaw errors exist plus minus 15 degree. A stability timer checks whether the misalignment persists for a short continuous period before acting. This prevents unnecessary movement caused by small temporary wind fluctuation and helps reduce motor wear. Finally, the cable safety limits at plus minus 80 degree. Whether the wind direction crosses the plus minus 80 degree mark, the system activates cable safe logic. Instead of continuing in the same direction and risking cable over twisting, the controller reverses the rotation directions to safely realign the turbine. This protects the internal wiring while keeping the nacelle correctly oriented. Together, these three cases ensure that the turbine aligns quickly, avoid unnecessary motion, and stays protected under all wind direction changes. This slide explains how the system selects the most reliable wind direction source using a priority-based control logic. The process begins with the wind vane, which is always given the highest priority. The system stays in vain mode as long as the vain reading and their AI prediction remain valid. Only when the vain signal becomes noisy, unavailable, or invalid does the controller switch to the next source, the live API data. If the both vain and live source fail, the system automatically fails back to AI prediction values, either vain AI or live AI, depending on which dataset was previously active. This ensured that yaw alignment continues without interruption, even during sensor faults or internet issues. The controller also checks every 5 seconds for source recovery. Whether a higher priority source becomes available again, the system immediately switches back to it. This rapid recovery process ensures continuous, stable, and fault tolerant yaw operation under all conditions. Overall, this priority logic guarantees that the turbine always uses the most accurate source available while maintaining smooth and reliable alignment. This slide shows the hardware used in the small yaw control system. The main controller is the Arduino Uno R4 Wi-Fi, which handles all the data processing, Wi-Fi communication, and motor control. For measuring wind direction, the system uses the RSFX JTO5 wind vane, which gives continuous analog readings. The nacelle is rotated using a NEMA 17 stepper motor, and the TB 6600 motor driver provide the power and control needed for smooth and accurate movement. All of these parts are connected to a small demo wind turbine, which allows testing of AI alignment, source switching, and AI prediction. This simple hardware setup acts like a smaller version of a turbine, helping confirm that the yaw control and AI prediction work correctly in real condition. This slide and the next slide is discuss about the output from microcontroller. In condition 1, vane mode is active. The wind vane is working normally, so the system stays in vane mode active. Since vane data has the highest priority, the motor aligns the nacelle based on the vane direction around 270.5 degree west. All data sources, vane, live, and forecast are available, and the system report no transition or reconnection. This represents normal operation with the vane provided the most accurate real-time direction. Second condition, vane mode active, network loss. In this condition, the system is still in vane active mode, but the network connection is lost. The controller no longer receive live API data, but the vane is still functioning because the vane has top priority. The turbine continues using vane direction now around 281.5 degree WNW and ignore live data until the network reconnects. The status shows live equals to lost while vane and forecast remain okay. This confirms that the system can keep running even when Wi-Fi disconnects. Third condition is like live data mode active, network reconnected. In this condition, the Wi-Fi network reconnects. The controller detects the vane becoming temporarily unable or invalid, so it transitions from vane mode to live data mode active. The source priority is still vane live forecast, but because the vane is not available, the controller now uses live API data showing a wind direction of 270 degree W. The status shows vane equals to loss and live equals to OK, and Wi-Fi reconnects increase to 1. This verifies that the system can automatically recover and switch to the next base sources. Continuing with the microcontroller output, this slide shows two additional operation conditions that demonstrate how the system intelligently switches between different data sources. In condition 4, that means return to the vane mode after live data operation. In this condition, the live API data was active earlier, but now the vane has come back online. Since the vane has the highest priority, the controller immediately switches back from live mode to vane mode. The yaw motor begins using the vane reading around 272 degree to realign the nacelle. All sources are now marked OK again, and the system resumes using the most accurate local measurement. This confirms that whenever the vane sensor recovers, the system always return to it automatically. The condition 5 is forecast mode active when all live inputs are lost. In the fifth condition, both the vane and the live API has become unable. The Wi-Fi connection also fails temporarily, so the controller cannot retrieve real-time weather updates. At this point, the system switches to the third failback option, forecast mode. It uses the forecast direction around 250 degrees to keep the turbine aligned. Even when all live inputs fail, the status clearly shows that vane equals to lost and life equals to lost while forecast remain okay. This demonstrates that the system is designed to maintain air control even under the worst case conditions. These outputs prove that the smart air control system maintains continuous operations through multiple failure scenarios, always selecting the best available source to protect power production and system reliability. This slide explains the software model built in MATLAB Simulink to test the smart air control system. The first part is the wind environment subsystem shown in blue. It generates realistic and changing wind direction and speed using vane, live and forecast data. It allows accurate testing of how the system reacts under different wind conditions. Next is air controller subsystem shown in cyan color. This block keeps the yaw error within plus minus 15 degrees and applies the plus minus 180 degrees cable safe limit to protect the internal wiring. It continues adjust the nacelle to maintain proper alignment. The yaw mode selector subsystem shown in green shows between active air control and fixed heading mode. This makes it easy to compare how the turbine performs with air control versus without air control. Finally, the power output calculation subsystem, which is turbine's power curve to convert simulated wind speed into electrical output. This helps measure how much power is gained or lost under aligned or misaligned air conditions. Together, these four subsystems create a complete digital twin of the turbine, allows safe and accurate simulation of the air behavior before implementing it in hardware. Now I will discuss the power output when using the vane sensor under two conditions, with air control and without air control. Starting with the active vane system with air control, the turbine constantly adjusts its nacelle to follow the wind direction. At the beginning, the nacelle is facing the opposite direction, so the yaw error is very large and the turbine produces almost zero power during the first 50 to 60 seconds while alignment is improving. But once the nacelle start matching the wind and power begin to reaching about 2.8 kilowatt at 100 seconds and climbing to over 3.5 kilowatt as the yaw error becomes small. The plus minus 15 degree dead band is visible at the flat sections of the graph. While when the yaw error stays within this band, the controller avoid unnecessary rotation, which reduce motor wear but still maintain stable power. The best element occurs around 480 and 778 seconds, where the yaw error is almost zero and power peaks is about 3.67 kilowatt. In contrast, the case without air controls looks very different. Here the nacelle is fixed at 45 degrees and cannot rotate to follow the wind. Because of this, the yaw error stays large most of the time and turbine produce highly unstable power. For example, at around 80 seconds, the yaw error is nearly minus 92 degrees and power only and the output drops to zero because the wind is hitting the blade slightly. Power only increase when the wind direction briefly comes close to the fixed nacelle angle. One of these moments happened around 153 seconds, where the turbine reaches about 1.6 0.66 kilowatt. The highest peak of 3.69 occurs at around 275 seconds, but this is only because the wind momentarily aligns with the fixed nacelle. As soon as the wind shifts again, the output falls sharply, even abruptly to zero, and at about 323 seconds. So overall comparison is very clear. With air control, the turbine maintains alignment and produces smooth, high and constant power. Without air control, the turbine relies on random wind alignment, causes large fluctuation and frequent power loss. Now this slide I will compare the turbine performance when the system is using the live online weather source, both with or without air control. Live source with active air control. When the vane become unable, the controller automatically switches to the live sources. The yaw mode selector changes to 2, meaning the nacelle is now aligned based on real-time open weather map data. Around 9 seconds, a sudden shift in the nacelle direction to about 357.7 degree as the system transition from vane to live control, followed by a short stabilization period. After this, the yaw error decreases quickly. At 40 seconds, the error drops from nearly 180 to about 10 degree, and the turbine becomes produce 2.11 kilowatt. As the alignment improves, the output reaches 2.83 kilowatt at 100 seconds and about 3.51 kilowatt at 183 seconds. The plus minus 15 degree dead bands is clearly at 307 seconds, where the yaw error is about minus 14 degree. The controller does not move the motor, yet the turbine still produces 3.47 kilowatt. The best alignment occurs at 483 seconds, where the yaw error is almost zero and power reaches 3.7 kilowatt. During this alignment period, the nacelle remains almost still because the controller stops adjusting once alignment is correct. Overall, the live source ensure low yaw error, smooth alignment, and strong stable power output whether the vane is unable. And in contrast, when air control is disabled, the nacelle is fixed at 45 degrees, so it cannot rotate to the following wind. Even though the live source provides accurate wind direction, the turbine remains misaligned most of the time, which causes large yaw error and unstable power. There are brief moments when the wind direction accidentally line up with the fixed nacelle. At 33 seconds, the power reaches about 2.05 kilowatt, and at 157 seconds, it rises to around 1.68 kilowatt. The highest peak of 3.7 kilowatt occurs at 280 seconds when the wind direction is almost the perfect opposite of nacelle position. Similar short-lived peak appeared at 383 seconds and 523 seconds, but they do not last. Most of the time, the turbine is severely misaligned, resulting in frequent drop to zero power and very inconsistent performance. Without air control, even accurate live data cannot help the turbine maintain aligned. This slide I will compare the turbine performance when using the forecast source, both with air control and without air control. In figure 11 shows the forecast source active with air control. When both the vane and live online data are unavailable, the controller switches to the forecast source. The yaw mode selector becomes 3, indicating forecast based alignment. During the first 0 to 60 seconds, the wind and nacelle direction stays near 0 degree because the forecast data has not updated yet. Even with poor alignment and the yaw error close to minus 176 degree, the rising wind speed increases the power from 1.59 kilowatt to 2.45 kilowatt. Around 45 seconds, the forecasted wind direction jumps toward 359 degree, placing the wind nearly opposite the nacelle and dropping the power to 0 kilowatt. Once the forecast is stabilized, the the nacelle began following the predicted wind again. By 100 second, power rises to 2.79 kilowatt as alignment improve. The strongest performance happened around 243 seconds, where the yaw error reduced to just minus 2.57 degree, produce a maximum power output of 3.96 kilowatt. Later at 355 seconds, the system remains within the plus minus 15 degree dead band, still generating 3.47 kilowatt. Throughout the simulation, power rises to about 3.5 to 3.6 kilowatt during close alignment and drops when the forecast shift away. Overall, even both primary and primary input fail, forecast waste yaw control system still maintain reasonable tracking and stable power. Figure 12 demonstrate the forecast source active but without yaw control. When yaw control is off, the nacelle stays fixed at 45 degrees, so it cannot rotate to the following forecasted wind direction. In the first 60 seconds, all direction signal remains near zero due to lack of updated forecast, and power change only with wind speed. As soon as forecast update arrives, several misalignment begins at 86 seconds. Yaw error reaches minus 174 degree, produce about 2.8 kilowatt before falling again. At 140 seconds, the wind shifts to 313 degree, nearly 19 degree away from the fixed nacelle, causing power drop to 0 kilowatt. A brief optimal alignment occurs at 336 seconds, where the wind direction is almost perfectly opposite the nacelle, producing 3.69 kilowatt. But this lasts not momentarily. The pattern continues: short spikes of high power when the wind lines up by chance, followed by long period of very low output. With yaw control active, the forecast source can still guide the turbine and support the stable power. But forecast data typically has a 2 to 3 hour delays, means it is not represent the real time wind direction. Because of this, forecast based control is not reliable on its own, especially in fast changing wind conditions. This is why our system incorporates AI prediction to fill this 2 to 3 hour gap, provide real time direction estimate, reduce yaw error, and maintain continuous and accurate alignment. These slides present a comparison of power output for different yaw control modes using Vane live and forecast data sources under both active and disabled yaw conditions. Look at the table. The Vane in yaw active mode constantly delivered the highest and most stable power across all the time intervals. At 100 seconds, it produced 2.8 kilowatt, slightly higher than the live value of 2.83 kilowatt and the forecast value of 2.79 kilowatt. By 300 seconds, the Vane reaches 3.47 kilowatt, performing better than the live source at 3.46 kilowatt, while the forecast value of 3.51 kilowatt is close but does not maintain that level constantly. At 480 seconds, Vane active yaw continues to perform strongly at 3.69 kilowatt, matching or extending the other two sources. At 778 seconds, the Vane source achieves the highest power recorded in the simulation, 3.70 kilowatt, reinforcing its reliability as the most effective real-time input. In the simulation, wind direction changes rapidly and the plus minus 15 degree deadband prevents full correction, so maximum power is rarely reached. In real-world conditions, wind typically stays steady for long period, gives the turbine enough time to align correctly. As a result, practical yaw control turbine maintain better alignment and achieve higher energy output than what is seen in the fast changing simulation condition. So the next session covering AI training and AI based prediction will be presented by my groupmate Shoaib Mahmood.
To maintain continue AIing accurately with the wind direction and maintain a stable performance, we introduce AI based wind tracking system. So our AI based wind tracking system only works when the both physical wind vane sensor and live wind data from the nearby weather station are not available and AI prediction gives a short-term wind direction, predicted wind direction, which learn from the past wind direction behavior. In this table basically show how AI predict how AI train up and how AI predict the next available wind data. So based on the three most recent wind data, AI can predict the next data. Here T3 is the oldest data, T2 is the middle data, and T1 is the most recent data. So based on this three wind direction, AI train up and AI can learn how wind direction actually changing. So we also here use the sine and cosine data to circulate the nature of angle. And here we also used the wind speed data to help estimate directional stability. So in this graph it's showing how predicted match with the match with actual so it's showing the predicted curve almost overlap the actual values, showing a very close match. The circular prediction error stay within about plus minus 10 degrees, indicating a stable and consistent prediction. So the regression fit around is about 0.978, which meaning the model explained roughly 98% of the variations. So overall, this confirms that AI model is accurate enough and acts as a backup source when other input fail. Now this is the output of trained AI model. So here we can see the blue line indicates the AI predicted data, and the black and red line indicates the actual wind data and the air position. So here the actual position and the actual wind direction are the overlap. That means the exactly follow the wind direction. Here the first priority is the wind direction from sensor or live weather station data. Okay. So the blue line indicates that this system properly predict wind direction predict the next available wind direction. So and the green line indicates the turbine output when the and the wind direction are closely matched, and purple line indicates the error, and the blue line indicates the efficiency. And this is the output of the microcontroller, and it shows which direction wind is coming, and the actual turbine's nacelle position, and the predicted wind direction. So when our wind source like vane and wind data from the next nearby weather station are not available, then this system rely on the AI predicted data, and also our turbine nacelle follow the AI predicted wind direction. In this slide, we are comparing our conventional wind turbine system and our proposed hybrid AI-based wind tracking system, and and air alignment system. So by using AI-based wind tracking system, we can eliminate some hardware component like a physical wind band sensor and transmitter and receiver, because in our system we can get wind data from the nearby weather station using API code, which is reduce 30 to 40% our maintenance cost, and as a result we will get around 3 to 5% more power generation by using this system. So in our system there are a few limitation, as online weather data come from nearby weather station, so it may not be a perfect match with the exact turbines locations data, unless we are using a GPS at the turbine location. Okay, if the both van and live data are lost, then the system rely only on the AI data, and its accuracy depends on the older data. So the mechanical wind vane can be affected by dust, moisture, corrosion, and other wind speed and low wind speed. And also a stable internet connection is needed for updating live data in every few seconds. So in future we want to integrate a GPS so that this system can automatically choose the nearest and most relevant weather station. Also we aim to develop a adaptive AI model that can keep learning from ongoing turbine performance. Also we will test our system on a larger turbine in different locations. So in summary, our proposed smart air control system deliver accurate air alignment, higher efficiency, and dependable operation under real world wind direction.